Hello everyone. Welcome back to Sally and Bytes. Imagine a time when businesses had to wait weeks for a report to arrive by mail. Now, the same data can appear on your screen within seconds through computer networks. From personal computers to powerful communication links, data communication is transforming the way we live, work, and connect with the world. In this video, we'll explore the basics of data communication, that is how devices talk. The invisible systems and signals that allow us to send text, audio, and video from one corner of the globe to another, instantly. Whether it's a business decision or a WhatsApp message, it all starts with understanding how data moves. Let's start with a simple question: what is data? Data is just a fancy word for information. It could be a simple text message, a photo or image of your pet, a video you recorded, a voice note, audio, multimedia files. Multimedia files are files that contain more than one type of media, like text, images, audio, video, animations, or graphics, all combined into one file or project. Even a bunch of emojis. And in digital communication, data is the message. In the digital world, data travels between devices. One device acts as the sender, the one sending the data, and another acts as the receiver, the one getting the data. As long as both devices understand the format of the message, it counts as data. So yes, when you send a hello message from your laptop to your friend's phone, that's data being sent from one device to another. Data is the message that travels between devices. Let's see how computers represent data. Computers only understand zeros and ones, also called bits. So everything must be turned into a pattern of zeros and ones for the computer to store, read, or process it. Text, letters and words. When we type something like hello, the computer sees a bunch of zeros and ones. Each letter is changed into bits using a system, kind of like a code language for computers. The two most common ones are ASCII, American Standard Code for Information Interchange, and Unicode. ASCII is a character encoding standard used to represent text in computers and other digital devices. Each letter, digit, or symbol is assigned a unique number, from 0 to 127 in standard ASCII, which is then stored and processed in binary, zeros and ones. Unicode is a modern character encoding system that supports many languages, and even emojis. Example: the letter A in ASCII becomes 01000001. Numbers 0 to 9 and beyond. Numbers are easy, right? Like 1, 2, 3, but to a computer, each number is also just a pattern of bits. Guess what? Numbers also use ASCII or Unicode to be stored. So, the digit 5 becomes 00110101 in ASCII. Images, pictures and pixels. Have you heard the phrase "a picture is worth 1,000 words"? Well, to a computer, a picture is made up of lots of tiny dots called pixels. Think of a pixel like a Lego block. Thousands of pixels come together to make the full image. Each pixel has a color, and that color is represented by, you guessed it, bits. For example, a black and white image needs only 1 bit per pixel, 0 or 1. A grayscale image might need 2 bits per pixel, like 00 equals black, 11 equals white. A colorful image needs 24 bits per pixel, that's millions of colors. So, more pixels equals more detail equals more memory needed. Common image file types: .jpg, .png, .bmp. Audio, sound waves turned into data. Think about your favorite song. How does a computer store it? Audio is recorded as waves, but since computers can't understand waves, they convert sound into numbers. They take tiny snapshots of the sound, called sampling, and turn them into numbers, which are stored as bits. Audio is continuous, not broken up like letters or numbers. The more bits per second, the clearer the sound. Video, moving pictures with sound. A video is just lots of images shown quickly, like a flipbook. Add some audio to it, and you've got a movie. Every frame of a video is like an image, with pixels, and the audio part is stored just like music. So, a video equals many images plus sound, all represented as bits. What is communication? Let's start with something super simple: communication. Communication is the process of sending and receiving information. And guess what? You're doing it all the time. When you tell your friend a joke, that's communication. When you send a text like "What's up?" that's also communication. Even when you're watching a video or listening to music, your device is receiving information. So in short, communication is just one person or device sharing information with another. Now, let's see, what is data communication? Now let's bring in the tech twist: data communication. Imagine this: you send a photo from your phone to your friend's phone. What really happens? Your phone talks to your friend's phone using signals. These signals carry your photo, also known as data. So, data communication is how electronic devices share information. It's the same as regular communication, but instead of people talking, it's devices exchanging zeros and ones, bits of data. And they don't use voices, they use cables, like Ethernet, Wi-Fi, wireless signals, Bluetooth, for short distances. For example, when you stream a video on YouTube, streaming video on YouTube means broadcasting a video live over the internet. Your device sends a request to YouTube server. YouTube server sends back data, frame by frame, sound by sound. Your screen shows the video, and your speaker plays the sound. That's data communication in action, devices sending and receiving data to keep things working smoothly. It's how phones talk, how computers connect, and how the internet works. Data communication means the exchange of data between two devices through a transmission medium like cables, optical fibers, or wireless mediums. What's needed for data communication? For data communication to happen smoothly, there needs to be a system. This system includes hardware, like your phone, computer, server, router modem combo, switches, network cables, Wi-Fi antennas, and satellites. Software, the programs and apps that manage sending and receiving data, such as messaging apps, email clients, web browsers, and networking protocols. Let's see the important features of a good communication system. Delivery, data should reach the correct destination and not go to the wrong place. Example, imagine you record a voice note to tell your best friend a secret. If that voice note accidentally goes to your class group chat instead, it's a delivery failure. The data, your voice note, didn't reach the right person, and that can lead to confusion or even embarrassment. Accuracy, data should be received exactly as it was sent, without any changes, errors, or corruption. Example, imagine your teacher emails you your test score, and you actually got 95 out of 100. But due to an error in transmission, the number gets changed and shows up as 59 in your inbox. That would be really upsetting, right? This is why accuracy in data communication is important, so that what's sent is exactly what's received, with no mistakes in between. Timeliness is data should arrive on time, exactly when it's needed, not too late. Example, think of a live online class. If your teacher's video or voice arrives 10 seconds late, it feels weird, right? You might hear the teacher ask a question, but by the time you hear it, they're already explaining the answer. That delay can be really confusing and makes it hard to keep up. That's why timely delivery is super important in things like video calls, online games, and live chats, because every second counts. Jitter, data should arrive at regular, steady intervals, not too fast, not too slow, and definitely not all over the place. Example, imagine you're watching a YouTube video. Suddenly, the video freezes, skips, or jumps ahead while you're watching. That's because the packets, small pieces of the video, aren't arriving evenly, some are coming late, and some early. This uneven arrival of data is called jitter, and it can make videos and live streams really frustrating to watch. That's why a smooth, steady flow of data is super important for a good experience. Let's see the components of data communication. To make digital communication possible, 5 key components must work together like a team. Sender. The device that sends the message either locally or globally. It can be a computer, workstation, video camera, or mobile phone. Example, your phone when you send a WhatsApp message. Receiver. The device that receives the message. It can be a computer, workstation, television, or mobile phone. Example, your friend's phone when they receive your WhatsApp message. Transmission medium. The path through which the message travels, it can be wired or wireless. Examples, Wi-Fi, mobile network, fiber optic cable, Bluetooth. Message. The actual data being sent, it can be text, an image, audio, or video. Example, the happy birthday message you typed and sent. Protocol. A set of rules that both the sender and receiver follow to understand each other. Just like we follow grammar rules in a language, computers use communication rules called protocols. Example, TCP/IP, the standard set of rules that allows devices to communicate over the internet. Let's see the key terms of data communication. Channel, the highway of data. Imagine you're driving your bicycle on a road to deliver a letter to your friend. That road is the path you travel. In data communication, we call this the channel. A channel is a communication path through which the data is transmitted from the sender device to the receiver device. A channel is just the path the data takes from one device, like your phone, to another, like your friend's phone. It could be cables, Wi-Fi, or even optical fibers. Example, when you send a video on WhatsApp, the internet is the channel that carries your data to your friend's phone. Bits per second, BPS, the speed of communication. Okay, now think of water flowing through a pipe. The more water that flows each second, the faster you fill a tank. Data works the same way. Instead of water, we send bits, the smallest unit of data. You can think of a bit like a simple yes or no, or a 0 or 1. So, the speed of data is measured in bits per second, or BPS. It tells us how many bits can flow through the network in 1 second. For example, let's say your phone sends 1000 bits in 1 second, that's 1000 BPS. Now imagine it can send 1 million bits per second, that's 1 megabit per second, way faster. So, the higher the BPS, the faster your data travels. And that means quicker downloads, smoother video calls, and zero lag in your games. You've probably heard of internet speed in bits per second, but have you ever heard of something called Baud? Imagine you're at a party with disco lights flashing, every blink is a change in signal, on, off, on, off. That's exactly how Baud works in the digital world. Baud is the rate at which a signal changes on a wire, like blinking lights. So, if the signal changes once every second, that's 1 baud. If it changes 1,200 times in 1 second, that's a baud rate of 1,200. Let's see an example. Let's say your connection has a baud rate of 1,200, that means the signal is changing 1,200 times every second. And if each signal change represents 1 bit, then 1200 baud equals 1,200 bits per second. But here's a fun fact, with advanced tech, one signal change can carry more than 1 bit. That's when BPS and baud become different. But don't worry, just remember, baud equals how often the signal changes. BPS equals how much data is sent. Bit rate versus baud rate. Let's take a closer look at this graph. In this image, you can see the signal changing 3 times, each change carries 1 bit, like 1, 0, 1. So, in 1 second, we have 3 signal changes, that's 3 baud. 3 bits sent, that's 3 bits per second. Here, bit rate equals baud rate, because 1 signal equals 1 bit. Now check out this image, same 3 bits, 1, 1, 0, but look at the signal changes, there are 6 changes. That's 6 signal elements, so baud rate equals 6. Still only 3 bits sent, so bit rate equals 3 bits per second. This means, more signal changes don't always mean more data. Here, each bit is split into 2 signal changes. So remember, bit rate is how much data is sent, in bits. Baud rate is how many times the signal changes. Sometimes they're equal, sometimes they're different, especially when advanced encoding is used. Bandwidth, how wide the highway is. What if the road had 10 lanes instead of 1? More cars can go at once, right? That's bandwidth, the amount of data that can be passed along a communication channel in a given period of time, 1 second. That is, it measures the information carrying capacity of a line or a network. It is the difference between the highest and lowest frequencies allowed on a transmission media. Telephone cables, for example, have a lower bandwidth than fiber optic cables. They can transmit a lower range of frequencies. High bandwidth allows transmission of many signals at once. On a monitor screen, high bandwidth provides a sharp image. Formula is bandwidth equals FH minus FL, where FH and FL are the highest and lowest frequencies. The measuring unit is Hz Hz. Let's see an example. If the highest frequency is 80 Hz and lowest is 50 Hz, what is the bandwidth of a signal? B equals FH minus FL. B equals 80 minus 50 is equal to 30 Hz. Latency or delay is the total time taken for data to be transmitted from the sender to the receiver. Latency equals propagation time plus transmission time plus queuing time plus processing delay. Transmission time. Transmission time is the time it takes to place the complete data packet onto the transmission medium. Transmission time equals message size divided by bandwidth. Propagation time. Propagation time is the time it takes for a single bit to travel from the sender to the receiver. When the sender sends a message, it consists of a sequence of bits, zeros and ones. This time depends on the distance between the sender and receiver and the propagation speed of the medium. Propagation time equals distance divided by propagation speed. Queuing time. Queuing time is the time a message spends waiting in queues at intermediate or end devices before being processed or transmitted. There is a lot of network traffic. Intermediate devices, like routers, may hold the data temporarily, leading to increased queuing time. Queuing time is not constant, it increases with network congestion. Processing delay. Processing delay refers to the time taken by a node, device, to process the message. This includes operations such as error checking, examining the packet header, and determining the forwarding path. It occurs at both the sender and intermediate devices before the message reaches the receiver. Data and signals, what is being sent? Okay, so what's actually being sent? That's data, like your voice, a text, or a photo are stored in the form of zeros and ones which convey some special meaning to the computer system. But devices don't understand language, they understand signals. When this data is transmitted from one place to another, it is converted into signals. Signals are like messengers carrying the data. They are electrical or electromagnetic codes made from zeros and ones, binary language. Example, typing high is turned into 010010001101101001 before being sent, and the signals carry it across the channel. Communication or transmission media. The carrier. Now, how is the signal actually carried? That's the job of the communication media, like the vehicle that carries a parcel. Communication media is the way of transmitting the signal from one place to another. Communication media is also known as transmission media. It plays an important role in sending and receiving of data to and from the sender and receiver. It can be wired, like Ethernet cables, wireless, like Wi-Fi or Bluetooth, or fiber optic, which uses light. Example, sending a voice message? Wi-Fi is your wireless media. Watching YouTube via fiber broadband? Fiber optic is your media. Data transfer rate. The speedometer. It tells us how fast data is moving from sender to receiver. It's usually measured in bits per second, BPS, bytes per second, BPS, or Baud, kilobits per second, kbps, megabits per second, mbps, gigabits per second, gbps, terabits per second, tbps. 1 kilobit per second equals 2 power 10 bits per second equals 1024 bps. 1 megabit per second equals 2 power 20 bits per second equals 1024 kilobits per second. 1 gigabit per second equals 2 power 30 bits per second equals 1024 megabits per second. 1 tbps equals 2 power 40 bits per second equals 1024 gigabits per second. Let's see an example. If you upload a text document at the rate of 10 pages in 20 seconds, each page having 1,600 characters, and each character equals 8 bits, what will be the required data rate of the channel? Formula: data rate equals total bits divided by time. Your data rate equals 10 pages times 1,600 characters times 8 bits, divided by 20 seconds, that's equal to 6,400 divided by 1024 bps equals 6.25 kilobits per second. For example, if your internet speed is 100 megabits per second, you can download a movie much faster than someone with 10 megabits per second. Devices don't talk like humans, they use data, signals, and communication media to send messages super fast. Let's see the types of data communication. Direction of flow. Depending on how data flows from one node to another node, there are 3 types of data communication. Simplex communication. Direction of data is unidirectional. That means data flows in one direction only. One device transmits, and the other receives. Example: a keyboard sends input to the computer. Think of it like this: the keyboard is connected to the CPU and sends data to it. However, the CPU doesn't send any data back to the keyboard. So, the communication is always one-way, like the one-way street. Some more examples of simplex communication are: television broadcasts. The TV station sends signals to your television, but your TV does not send anything back. Loudspeaker systems. An announcer speaks into a microphone, and their voice is sent through an amplifier to all the speakers. The audience does not send any sound back to the microphone. Fire alarm systems. Many fire alarm systems work in a similar way. The central system sends signals, like an alert or siren, but no data is sent back to it from the alarms. Half-duplex communication. Data flows in both directions, but only one direction at a time. That means, half-duplex communication support two-way traffic but in only one direction at a time, like a one-lane bridge. Example: walkie-talkies. In a walkie-talkie, we can both talk and listen, but not at the same time. When one person is speaking, the other must wait to reply. Now look at this image. Computer A sends information to computer B. At the end of transmission, computer B sends information to computer A. Computer A cannot send any information to computer B, while computer B is transmitting data. Full-duplex communication. Data flows in both directions at the same time. Devices can send and receive data simultaneously. It is two-way or bidirectional communication in which both devices can send and receive data simultaneously. It is like a two-way road where vehicles can go in both directions at the same time. Example: telephone networks operate in full-duplex mode when two persons talk on telephone line, both can listen and speak simultaneously. Now look at this image. Both computer A and computer B can send and receive data simultaneously. Thanks for watching. If you enjoyed learning how devices talk, give a thumbs up, hit subscribe, and share it with your techie friends. See you next time.